This video is going to discuss hypothesis testing, another form of statistical inference, and hypothesis testing where the parameter of interest is the population proportion. So hypothesis testing, you have two hypotheses. You have your null hypothesis, which is either what you believe to be true or what has been claimed to be true, or what you hope to be true. And you have an alternative hypothesis. The null hypothesis has this zero here. And you will state it this way. When you are asked to state the hypotheses, you need to use this mathematical notation to do it, not words. And there are alternative hypotheses. So you're going to state a null hypothesis and an alternative hypothesis. And what hypothesis testing does is it takes the null hypothesis and assumes it's true. Let's build this based on this being true. And then let's look and see if there's evidence in favor of the alternative hypothesis. So the alternative hypothesis can be one of three things. It can be a one-sided alternative that's saying, no, P isn't equal to P sub 0, it's greater than P sub 0. We want to see if there's evidence to show that it's greater. Or it could be, nope, it's not equal to, it's less than. We want to see if there's evidence to show that it's actually less than. Or it could be a two-sided alternative. We just want to see if there's evidence to show that it's not equal to. And each of those is going to do something different to how we execute and interpret the results of our hypothesis test. So remember, there's a z-statistic that results from standardizing population proportion. P hat minus P over the square root of P times 1 minus P over N. So if we assume that P is equal to P sub 0, we can put P sub 0 in the place of P. So what in effect this means is we have gathered data, and from the data we've gotten a P hat. And if we put that into this formula along with the P sub 0 from our null hypothesis, we get a test statistic Z. And we can put that on the normal curve. Now think for a minute, what is the mean of that normal curve? It's P sub 0. That is what we have assumed to be true. And the z-statistic is on that normal curve with a mean at P sub 0. And we're basically looking to see how likely is it that we would get that z-score if this were actually the case. Is it way out in the tails and really unlikely? Or is it close enough to that mean that we're like, not unlikely enough that we can write it off? That's the whole basis of hypothesis testing. So the p-value, now don't get messed up when you're doing population proportion between p-value and p being the population proportion. The p-value is the probability of getting a value as extreme or more extreme than what you got. So again, it's that whole concept of how unlikely is this. If it's what we call a right-sided hypothesis test, P greater than P sub 0, then we want to know what's the probability of getting a value as large or larger than what we got. In other words, how far out in that right tail is it? On the other hand, if it's a left-tailed, one-sided hypothesis test, then we're looking at the probability of getting a value as small or smaller than that observed test statistic. And if it's two-sided, then we have to look in both tails. And we'll do that by taking the z-score and finding how far out that is in one tail and doubling it so we cover both tails. So think back to the normal distribution work that we did. When we have those z-values and we want to know how extreme they are, we want to find the probability that something is in those tails, which is the area under the curve in those tails. This concept is absolutely key to understanding hypothesis testing. The understanding of a p-value and what it represents is absolutely key to this whole process. Here's another way of looking at it for those of you who are a little more visual. I think this really helps. Again, we're testing this hypothesis and computing this z statistic. If our alternative hypothesis is this, then we want to know what's the probability that z is greater than this z-value. In other words, what's the probability that we're in this orange tail? It's hard to tell, but this is a little yellower and this is a little oranger. We want to find the probability that we're in this tail, which is the area under the curve right there. If we're in a left-sided hypothesis test, we want to know the probability that we're in this curve that's less than the z-value. And if we're in a two-sided, I don't really care which side it's on, I just want it to not be equal to, then we have to take the area from one side and double it to cover both of our tails. This is a really important piece. It's just down at the end here, but I want you to make sure you write this down somewhere and remember it, because you might see a problem where this criteria is not met. And you cannot use this kind of hypothesis test when this criteria is not met. The criteria is this: the sample size n needs to be large enough so that when you multiply n by p sub 0, your assumed population proportion, and when you multiply n times 1 minus p sub 0, both of those arithmetic expressions, when figured out, give you 10 or larger. You have to have that criteria met to do this kind of test.